In western Kentucky, workers have spent years taking apart an electrical system built for a machine that no longer exists. The machine was a uranium enrichment plant. Its 4 switchyards could support as much as 3,000 megawatts. 18 high-voltage lines entered the site. Transformers and more than 80 circuit breakers fed process buildings so large that their roofs covered dozens of acres. Then enrichment stopped. The plant's electric demand fell from the scale of a major city to roughly 10 or 12 megawatts. The old switchyards were shut down. Some of their steel, oil, towers, and conductors were removed while the federal government settled into a cleanup expected to last for decades. Now the power is coming back. In July 2026, the Department of Energy selected a private group to develop a 1.8 gigawatt artificial intelligence campus on portions of the Paducah site. NextEra Energy plans 2 gigawatts of new grid-connected gas generation, transmission upgrades, and as much as 2.6 gigawatts of battery storage. Brookfield would develop the data center. The expected investment is more than $100 billion. On paper, this looks like the answer to the AI power problem. Put the computers on an old federal industrial site. Bring more generation than the campus needs. Let private capital pay for it. Send the excess power to everybody else. But none of those verbs means the same thing. Selected is not built. A gigawatt of battery power is not a promise about how long the battery can run. Grid connected is not electrically private. And a project on federal land does not make the federal cleanup disappear. So what would it take for this campus to bring its own power without bringing its risk to everyone around it? The answer starts with the old machine, because Paducah has tried industrial electricity at this scale before. The Paducah Gaseous Diffusion Plant began operating in 1952. It was built to enrich uranium, first for the country's defense program and later as feed for commercial nuclear fuel. Natural uranium contains different isotopes. The useful one for most reactors, uranium-235, is a small fraction of the total. At Paducah, uranium was converted into uranium hexafluoride gas and pushed through porous barriers. Molecules containing the lighter isotope passed through at a slightly different rate. The difference at one barrier was tiny, so the plant repeated the step again and again across a cascade of stages. That repetition made gaseous diffusion brutally power-hungry. Compressors had to keep an immense volume of gas moving. Motors, pumps, cooling systems, control gear, and process equipment had to run with it. A 2012 Department of Energy presentation said the plant usually consumed between 700 and 2,000 megawatts, depending on production and power prices. It was designed to reach 3,000. The electrical system matched the scale of the process. 4 switchyards served the major process buildings. Power arrived at 161,000 volts. Large transformers stepped it down. Underground feeders carried it into the plant. A web of circuit breakers could isolate faults before one failure spread through the cascade. That is why Paducah interests a data center developer. This was no factory with a convenient parking lot. It was organized around a continuous industrial load measured in gigawatts, with transmission corridors, waterworks, roads, and security. But history can be misleading. The old system proved that the region once moved that much power. It does not prove the old capacity is waiting behind a switch. Commercial enrichment ended in 2013. The facilities returned to the Department of Energy the following year. With the cascade silent, the cleanup mission needed only a small fraction of the old supply. DOE built a smaller substation and bypass distribution system. It took the last old switchyard offline and began dismantling equipment that cost money to inspect, protect, and maintain. At one point, the site had enough electrical capacity to serve a city. Today, much of that machine is evidence. The buildings did not become harmless when the compressor stopped. 6 decades of enrichment and support work produced radioactive, hazardous, mixed, and ordinary industrial waste. Operations contaminated soil, groundwater, and surface water. The federal government began environmental work in the late 1980s. The site entered the Superfund National Priorities List in 1994. One of the best-known problems is trichloroethylene, or TCE, a solvent used to clean machinery. DOE says the Paducah site contains one of the largest groundwater contamination plumes in its environmental management complex, although pumping, treatment, and source work have reduced or reversed parts of its movement. Cleanup has no single finish line. DOE currently estimates complete remediation around 2065 at an approximate total cost of $17 billion. That cost did not come from the data center proposal. It belongs to the old enrichment mission. Keeping those two ledgers separate matters. A new private tenant might create useful revenue, jobs, and demand for reusable land. It does not inherit every federal liability simply by signing a lease. The federal government cannot transfer away its cleanup obligations with a press release either. The physical work is still visible. Crews finished segmenting nearly 500 large pieces of process gas equipment from one building in early 2026, then shifted attention to another. Pump and treat systems continue moving contaminated groundwater through treatment units. Regulators are still deciding how buildings, environmental media, and future waste disposal fit together. DOE calls its current approach Decision 2029. The idea is to collapse more than 50 separate cleanup decision documents into 5 coordinated decisions. The department says this could bring final cleanup decisions forward by as much as 25 years and free suitable land for reuse sooner. That is not the same as finishing cleanup 25 years early. It means making the regulatory decisions sooner than carrying out the work those decisions require. The AI campus would not replace the cleanup site. It would develop alongside it while other areas remain controlled, treated, dismantled, or restricted. The exact parcel matters. So do its environmental condition, utility boundaries, access routes, and long-term controls. Those details have not yet been laid out in the public announcement. Until they are, an aerial photograph of the whole Paducah complex cannot tell us where the servers will sit or which old infrastructure can actually be reused. The federal process began before the $100 billion headline. In November 2025, DOE asked companies for offers to build and power AI data centers at Paducah. The solicitation said applicants would fund their projects, secure permits and utility interconnection, operate them, and eventually decommission them. Proposals would be judged on technical readiness, financial strength, and their plans for regulatory approval. On July 29, 2026, DOE announced its selections. Brookfield was selected to develop and operate the data center campus. NextEra Energy was selected to build and own the dedicated energy infrastructure. Big Rivers Electric would provide wholesale power. Jackson Purchase Energy Cooperative would provide retail service. Paducah Power System would participate as a community partner. The proposed numbers are enormous. The campus would reach 1.8 gigawatts. NextEra plans 2 gigawatts of new grid-connected natural gas generation, upgrades to transmission, and up to 2.6 gigawatts of battery storage. DOA expects more than $100 billion of private investment, about 8,000 construction jobs, and 600 permanent jobs. Construction is expected to finish in 2031. Every one of those statements describes a future condition. The department has selected partners, but the public announcement does not name the companies that will fill the data halls with computers. It does not provide a final lease, a gas plant permit, a pipeline route, a transmission study, a battery energy rating, or a water balance. DOE also says the power service agreement remains subject to approval by the Kentucky Public Service Commission. That does not make the project hollow. Major developments begin with incomplete documents. It means the project is now in the stage where a clean announcement has to become several enforceable systems at once. The data center, power system, and utility contract each have separate construction and financial schedules. One delay can push against the other two. The story is not that Paducah has one deal. It is that Paducah needs a stack of deals that all work together. Start with the simplest comparison. The proposed campus load is 1.8 gigawatts. The proposed gas fleet is 2 gigawatts. At nameplate capacity, the generation number is 200 megawatts larger than the campus number. That difference supports DOE's claim that the project could produce more power than the campus needs. It does not prove excess power will be available every hour. Power plants consume some of their own output and go offline for maintenance. A campus may ramp in stages rather than arrive at full load on day one. Transmission has its own schedule. A 2 gigawatt nameplate beside a 1.8 gigawatt customer is the start of an operating model, not the result. The batteries add flexibility, but their headline requires a different unit. Gigawatts tell us how fast a battery can deliver power. Gigawatt hours tell us how much energy it can store. A 2.6 gigawatt battery that can run at full output for 1 hour stores 2.6 gigawatt hours. If it can run for 4 hours, it stores 10.4. The public Paducah announcement gives the power number, but not the duration. Without duration, we cannot calculate how long the batteries could carry the campus, how much gas generation they could replace during an outage, or how much excess energy they could shift into a grid peak. They might be designed for short grid response, several hours of peak shifting, backup support, or a combination. The engineering may eventually be excellent. The current number alone cannot tell us. Then there is the phrase grid connected. The gas plants are described as new and dedicated to the project, but they would connect to a regional electrical network. Big Rivers would sell wholesale power. Jackson Purchase would deliver retail service. Transmission upgrades would move electricity between generators, the campus, and the rest of the system. Electrons do not carry ownership labels. Operators balance injections and withdrawals across the network. The campus can have a contract tied to specific new plants without receiving a private stream of electrons from one turbine. When generation exceeds campus demand, the difference can flow outward. When a plant is unavailable or the campus arrives before all of its supply, the surrounding system may carry the difference, subject to the final contract and operating rules. This is why the project cannot be judged as an island. Its value depends on how it behaves while connected. If the plant's storage and transmission arrive on schedule, other customers may benefit. Each claimed benefit still needs a study, a meter, and a rule. Otherwise, the system has large machines and a hopeful subtraction problem. Paducah still has advantages that are hard to create on an empty field. The federal site covers thousands of acres in an industrial region near the Ohio River. DOE points to available land, transmission capacity, water infrastructure, and fiber connectivity. Roads and security already serve a complex federal mission. The surrounding community understands heavy construction. The historical water system shows the scale. DOE says the old plant used roughly 30 million gallons a day when it was operating and had treatment capacity around 30 to 32 million. Current site demand is closer to 3 million gallons a day. That does not mean 27 million gallons are reserved for AI. The condition of the intake, treatment plant, distribution system, permits, river limits, and competing uses all matter. Data center water consumption also depends on cooling design. A gas plant may have its own cooling requirement. The public announcement does not disclose the campus water demand or the final power plant cooling system. The electric story has the same shape. Paducah's old corridors and utility connections make it legible as a gigawatt site. But DOE spent years reducing and rerouting the enrichment-era system because maintaining 3 gigawatts of obsolete switchgear for a 10 megawatt cleanup load made no sense. Some towers and switchyard equipment have been removed or scheduled for dismantlement. The new announcement explicitly includes transmission upgrades. The developers are not walking into a preserved 3 gigawatt socket. They are choosing a place where the geography and history may make a new connection easier than starting with nothing. A gas fleet still needs fuel delivery. Transmission needs studies and construction. Server buildings can energize only when dependable power and delivery are ready. Paducah offers a head start measured in land, corridors, water access, and institutional experience. The size of that head start will be known when the engineering documents replace the historical photographs. DOE presents the project as privately financed and ties it to a federal ratepayer protection pledge. The pledge says large technology customers should build, bring, or buy new power, pay for delivery upgrades, accept separate rates, keep paying for infrastructure even when they do not use all of it, invest locally, and support grid resilience. Those are useful principles. They are not a power service agreement. The agreement going to the Kentucky Public Service Commission is where the principle becomes arithmetic. It can define the contract term, minimum demand charge, construction contribution, credit support, exit payment, fuel treatment, transmission responsibility, and how shared upgrades are allocated. If the campus reaches full load and operates for decades, a long-term customer can support the cost of new plants and wires. If the gas plants and transmission are built, but the computing tenant never arrives, the physical assets still carry debt and maintenance costs. A strong contract keeps that obligation with the project and its financial backers. There is also a timing problem. Grid upgrades can enter utility rates before a campus reaches full demand. Minimum payments and construction security can cover the gap. If the project ramps slowly, the contract needs to say whether the customer pays for reserved capacity or only the electricity it takes. Shared infrastructure makes the answer less tidy. A transmission line may serve the campus and improve service elsewhere. A new generator may sell excess power into the regional market. The project should pay the costs it causes, but customers who receive a measurable shared benefit may properly bear some share. The regulator's job is to test that allocation instead of accepting either extreme as a slogan. The federal cleanup sits on a different ledger. DOE's estimated $17 billion remediation program predates the AI project and will continue whether the campus succeeds or fails. A lease could help put suitable land to work. It does not make historic contamination a private data center cost unless the final documents assign a specific new obligation. So the who pays question has at least 3 answers. Private developers should pay for the campus and dedicated power system. Utility customers should pay only for benefits they actually receive through the regulated network. The federal government remains responsible for its environmental legacy. Keeping those ledgers separate is the difference between reuse and cost transfer. The number 8,000 is likely to appear in every public presentation. DOE expects roughly that many construction jobs. It expects about 600 permanent jobs after completion. Both numbers matter, but they describe different economies. Construction can transform local demand for electricians, pipe fitters, equipment operators, concrete, lodging, and transport for several years. 600 permanent positions would still be substantial, but a completed data center does not employ one worker for every construction job that disappears. Workforce programs and hiring commitments will determine how much of the benefit stays local. The physical burdens arrive in stages 2. Gas generation brings combustion emissions, noise, cooling questions, and fuel infrastructure. Transmission work affects land and construction routes. Batteries require emergency planning. The data halls change traffic, lighting, and water demand according to their design. That is why permits matter. They turn a rendering into measured equipment, modeled emissions, and operating limits. Paducah also has a history that makes promises about industrial afterlives unusually important. The enrichment plant delivered national security work and long-term employment. It also left buildings, solvents, radioactive material, burial grounds, and a cleanup stretching across generations. The new campus is not the old plant. Modern data halls and gas turbines present different hazards. Private companies are expected to fund and decommission their own infrastructure. Yet the old site gives the community a fair reason to ask what remains when the customer leaves. The 2025 federal solicitation anticipated that question. It made applicants responsible for decommissioning their projects. The final lease must show how that promise is secured. A sentence assigning responsibility is weaker than money, insurance, a bond, or another mechanism that still exists if a corporate entity fails decades from now. Paducah does not need certainty about the distant future. It needs contracts built for ordinary failure, delays, ownership changes, lower demand, equipment retirement, and a tenant that decides the next campus is cheaper somewhere else. The site has land and a workforce. The region has real electric history. Brookfield and NextEra have the scale to develop major infrastructure. New gas generation and storage arriving with a new load is more defensible than asking an existing grid to find 1.8 gigawatts from whatever happens to be available. But the project has not earned its ending yet. The final power service agreement should show who pays if the campus is late, smaller than planned, or cancelled. The transmission studies should identify which upgrades are dedicated and which provide shared benefit. The battery design should disclose energy capacity and operating purpose. Gas permits should show the actual turbines, emissions, cooling system, and fuel connection. Water documents should compare new withdrawals with the old system and current cleanup needs. The lease should define the parcel, environmental controls, rent, decommissioning security, and the boundary between private construction and federal remediation. Tenant commitments matter as much as equipment. A 1.8 gigawatt campus without committed computing customers is a plan for buildings. A 2 gigawatt power fleet without a dependable buyer is a merchant risk. When both sides arrive together under contracts that survive delay, the project begins to look like the promised private energy hub. There are several ways the schedule can unfold. The best case is synchronized. Campus buildings, gas units, batteries, and transmission enter service in matched stages. The customer pays from the moment capacity is reserved. Excess generation and storage support the network when available. Another case brings the power first. That can still benefit the grid, but the contract must keep the campus responsible for the facilities built in its name. A third case brings the computers first. Then the regional system carries more of the load until dedicated supply catches up. The operating agreement has to define the limit rather than discovering it during a tight season. The worst case builds shared infrastructure for a customer that never arrives and leaves the utility searching for another payer. That is the failure the ratepayer pledge claims to prevent. These are not predictions. They are the ordinary branches of a construction schedule. The Kentucky Commission will not decide whether artificial intelligence is good. It will decide whether the financial and electrical boundaries remain intact when reality differs from the base case. Paducah's old plant consumed electricity on the scale now associated with artificial intelligence. The important part of that history is what happened after the load disappeared. The switchyards did not vanish when enrichment stopped. Workers had to drain oil, reroute lines, cut equipment apart, secure contaminated buildings, and maintain a cleanup system for years. Infrastructure lasts longer than the customer it was built to serve. The proposed AI campus can learn from that without being condemned by it. Building new generation beside new demand is a sensible starting point. Using suitable federal industrial land may avoid pushing the same footprint onto untouched land. Batteries and transmission can make the system more flexible. A long-term private customer can pay for equipment that also strengthens the regional grid. So can Paducah's AI campus bring its own power without bringing its risk to everyone else? Not because 2 is larger than 1.8. Not because a battery has a large gigawatt number. And not because the project is described as private. It can do it if the generation and campus are built in matched stages, if the utility contract charges the project when capacity is reserved, whether or not it is used, if shared costs follow shared benefits, if the lease protects the cleanup mission, and if decommissioning security survives the companies that sign it. That is a much harder promise than building a gas plant. It is also the promise that makes this proposal worth watching. Paducah is not an empty site waiting for a new machine. It is a place still dealing with the last one. If the new project pays for its entrance, its operation, and its exit, the site may turn old industrial capacity into a useful second life. If those boundaries remain soft, a privately financed campus can still leave a public bill. The turbines will show whether the project can produce power. The contracts will show who carries it when the plan changes.